So we've seen that we can write functions as infinite series, but what is this good for? One use is in approximating functions, and to do that we use what are called Taylor polynomials. If we consider a function f of x, and instead of doing an infinite Maclaurin series expansion, we just do one up to some finite number n. As we increase n, it turns out we can get better and better approximations to the function. Let's consider cosine of x. So we saw that this was equal to the series 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial, and so on, all the way up to infinity. We can identify the Taylor polynomials in here. So t0 is just 1, t1 is equal to t0 because cos is even, so all the odd ones are equal to the even ones. So here we have t2, here we have t4, since t3 is equal to t2, the terms up to x to the 6, t6, and so on. Now, considering each of those in turn, let's plot them on a graph. And if we consider cosine of x and then plot on top of that t2, we can see this is just a parabola which approximates a function near the origin very well. But of course, far away from the origin, as we approach x of order 1, we can see this is a really poor approximation. Now look at t4. As we move away from the origin, this approximates the function better, but eventually diverges away from it again. Then looking at t6, the same behavior, t8, t10. By the time we get to t10, we can approximate the function all the way from the origin out to the bottom of the first trough at x equals pi, and so on. We can add on higher and higher order polynomials, and they approximate the function better and better the further we go from the origin. And the idea is if we had infinitely many of them, if we take t infinity, which is the full series, then we get exactly the whole function back. So we can see this in other examples. So if we take the example of the exponential function, we can see adding up different orders of Taylor polynomials approximates a function better and better far from the origin. And if we zoom out, they become poor approximations to the function. Or we could try this about another point. If we try the function log of 1 plus x around the point x equals 4, we can see the same behavior happening. Close to x equals 4, low order Taylor polynomials are good. Further away they become not so good, and so you have to add on more and more terms. Let's now consider a special example of a Maclaurin expansion, which is the binomial theorem. If we expand out x plus y squared, we know that this is x squared plus 2xy plus y squared. If we expand out x plus y cubed, we get x cubed plus 3x squared y plus 3xy squared plus y cubed. If we expand out x to the 4, we get a familiar pattern. And the numbers in there go 1, 4, 6, 4, 1. In the next line where we have x plus y to the 5, we have x to the 5 plus 5x to the 4y plus 10x cubed y squared and so on. And this may be familiar, the coefficients in this form what's called Pascal's triangle. Raising x plus y to some power, where that power is a positive integer, is a special example of what's called the binomial theorem. So let's derive the binomial series for the function 1 plus x to the power k. And we're not going to assume that k is a natural number. If I go through the procedure of calculating derivatives and evaluating them at the origin, a familiar pattern emerges. In this case, if we want to form the coefficients that we need for the Maclaurin expansion, what we need is the nth derivative at x equals 0 over n factorial. And this we can see by inspection that we're going to get on the numerator k times k minus 1 times k minus 2 times k minus 3 all the way to k minus n plus 1. And again we can see that by comparing. For the third derivative we go down to k minus 2. Now these coefficients are known as the binomial coefficient, and we write them as a special tidy notation as k choose n. And you'll see these come up a lot, the various combinatorics, and they're defined for n greater than or equal to 1 with the extra definitions, and of course we use, as usual, 0 factorial is equal to 1. Now in fact, in Pascal's triangle, where k is a natural number, this is equal to k factorial over n factorial into n minus k factorial. And in that case, the series will actually terminate, as we'll see. What we found is a very nice expression for the expansion of 1 plus x to the power k. And this is true now for all k in R. And this converges provided the modulus of x is less than 1. And you can go have a go at finding that out for yourself. If we just skip back to what the coefficients are when k is a positive integer, a natural number, then we can see that once we get to k equals n, this series will terminate because these coefficients will then all become 0. And we'll recover the result we would get from Pascal's triangle. We've already seen the first term of this when we've used the linear approximation to the function 1 plus x to the power k. Let's have a look at an example from special relativity. So the energy of a particle observed to be moving with a velocity v, which has a rest mass in its own rest frame of m, has an energy E equals gamma mc squared, where gamma is the contraction factor 1 minus v squared over c squared, where c is the speed of light. As v approaches c, this factor approaches infinity. Let's now use the binomial series expansion to find the low speed approximation. It's not 100% clear yet what to do, but let's have a look at this gamma factor in a bit more detail. That's the part we need to expand. So as v is small, what happens to gamma? Let's write this out like where k is explicitly minus 1/2. As we have just derived, we can just shove in the relative numbers into the binomial expansion that we've just seen. So we're doing a sum over binomial coefficients of minus 1/2 and n times minus v squared over c squared to the power n. And if we write out the first few terms of that, that's going to give us what we need, because if v is small, if v is much less than c, then if we consider the ratio of v over c to the 2n, this is going to tend to 0 as n tends to infinity. So these relative contribution of each term is going to get less and less important. So the first few terms then should give us a good approximation for a low velocity particle. So let's write out the first few terms is 1 plus 1/2 v squared over c squared plus 3/8 v to the 4 over c to the 4 plus 5/16 v to the 6 over c to the 6 and so on. Therefore, if we put this into the formula for the energy, which is gamma mc squared, first term gives us mc squared, Einstein's famous formula. The next term is 1/2 mc squared times v squared over c squared, leaving us with mv squared, the familiar kinetic energy. And then the next correction is the relativistic factor, 3/8 m times v to the 4 over c squared.